This screencast is about properties of light and terms associated with waves. So light moves as a wave, and some of the terms associated with waves are wavelength, which is the upside down looking y. It's a Greek letter lambda, and this is the distance between corresponding points on adjacent waves. So if you pick the top of one wave and you measure the whole way through the wave cycle until you get to the top of the next wave, or the bottom, or wherever you decide to start. Frequency is it's kind of a cursive looking V, but it is nu is the Greek letter, and it's defined as the number of waves that pass a given point at a specific amount of time, usually in 1 second. So if you pick 1 second and you measure how many waves go past that point, that is the frequency. So here is a graphic that shows some of the parts of the wave. You can see that the wavelength is from the top of this peak to the top of the next peak, and you can see the frequency would be, if you're measuring here and we measured a second, we'd see how fast or how many waves it goes by. Here is the amplitude. It can be measured the height from the midline to the bottom of the trough, or the midline to the top of the peak. And you see another number that you're going to need to remember is the speed of light. Here's another picture. You can see the peak, a trough. The node is considered the point where the wave goes above and below the midline. You have wavelength shown here and amplitude. Here's another graphic showing you the difference between a long wavelength and a short wavelength. And if you then take that a step further, and we are standing here on this post as one full cycle, this is a slow frequency and this is a high frequency. So frequency and wavelength are proportional. So if you have a short wavelength, you have a high frequency, and if you have a long wavelength, you have a low frequency. You can see the difference. Alright, so the equation that you're going to need to deal with light is C equals lambda nu, where C is the speed of light in meters per second, lambda is the wavelength of the wave in meters, and nu, or the V, is the frequency of the wave in 1/seconds, or hertz. Now, seconds shown with a -1 here is the same as 1/seconds, and that whole unit is the same as hertz. So you're able to take this equation and substitute the speed of light, which is a constant, and that will equal whatever wavelength you're dealing with, and you can find the frequency, or whatever frequency you're dealing with and you can find the wavelength. So we need to know the speed of light, and here is the actual value, but we're going to round it to the acceptable value of 3.0 times 10 to the 8th meters per second. A lot of times the wavelength is given in centimeters or nanometers, so be careful, you will probably have to convert some metric units. Here's a helpful reminder: 1 meter is 100 centimeters, and 1 meter is 1 times 10 to the 9th nanometers. So here's a sample problem. A sample of light has a wavelength of 3.4 times 10 to the -9th meters. What is the frequency? Alright, so we're going to use our equation, and we're going to plug in our number for the speed of light and the wavelength that they gave us, and we will then divide to find the frequency, and you get an answer of 8.8 times 10 to the 16th hertz, or 1/second. So this equation is pretty simple. You just plug the numbers in and solve. You could be given wavelength and asked to find frequency, or given frequency and asked to find wavelength. Okay, so make sure that you remember that equation, C equals wavelength times frequency, and that you remember the speed of light. And that should make this equation pretty easy to solve.